Algebra 2 Note 7.3, using functions involving e. So there is a number e, and we're going to be using it as the base today for our functions. So base, remember, that's going to be the part that gets the exponent. And because we're working with exponential functions, that exponent will be an x. That's going to be our variable part. So when we look at the natural base e, or the number e, it is a special number like pi. So pi is an irrational number as well. Pi we know is 3.14, but it goes on forever. We cannot write it as a fraction. Same thing with e. So e to 3 decimal places would be 2.718. It is the base rate of all continuous growth or decay processes. So if you look at continuous growth for money, if you look at continuous growth for population or bacteria, all of those, it turns out that they have this number e in common. So it's really pretty cool. So first, we're just going to play around with it and use it like we would a regular variable when we're working with exponents. So if I have the same base, I can add my exponents. 9 plus 6 would be 15. So this would simplify as e to the 15th power. For example, b, we could divide the 60 divided by 12, and that's going to give us 5. And then I can subtract my exponents for e. 8 minus 3 would be 5 as well, so 5e to the 5th. Here's example C. So remember, we can distribute exponents over multiplication. So negative 10 gets raised to the 3rd power, and this e to the negative 5th gets raised to the 3rd power. So negative 10 to the 3rd would be negative 1,000. 10 times 10 times 10 is 1,000. And when I have a power to a power, I multiply my exponents. Negative 5x times 3 is a negative 15x. So that's just to give you an idea about how e works. Like I said, we're just using exponential rules. So now we're going to practice using it on a calculator. So your E button on your calculator, it could be e to a power already, or it could just be the number e by itself. On my calculator, I have to do second to get to it. It's with the ln. So mine, if I find ln, which is actually natural log, right above it, I have an e raised to the x power button, and I have to do second to get to that. So I'm not sure what yours is going to look like. And so for me, I would press this button first, and then I would do the 6 for my exponent. But for you, it might not be like that. You might have to put the 6 and then the number. So I'm going to go ahead and give you the answer so that you can play around until you can get your calculator to give you this answer. So you'll have to figure out, do you press E first and then 6? Do you do 6 and then E? Where is that button located? So I'm going to give you a bunch of decimal places so you're really sure that you're doing it right. So this is what it should come out as. And then we thought it would be good to play around and give you a negative exponent as well, something that's a decimal, and you should get this here. So if you could not find that button, or if you didn't have it, remember E is about 2.718, so you could do 2.718 to the 6th power, if you could figure that out. But it's going to be way more accurate to use the E button, because this is only 3 decimal places, and I've listed 7 here on my answer. So if you raise 2.718 to the 6th power, it's not going to be exactly like this, but it'll be pretty close. So here is some information about natural base functions that I just copied verbatim from the textbook. So we told you about how we were using e as a base. And so we still have that coefficient that we're multiplying by a that's going to do a vertical stretch or shrink. And our exponent is x, but now we have an r times our x. So that is going to be our natural base exponential function. It's a long name. So it's an exponential function, but now we have e for a base, so natural base. And then we have some information here. If a is greater than 0 and r is greater than 0, we have growth. If a is greater than 0 and r is less than 0, we have decay. And then I just quickly drew some diagrams here to show what it would look like if we had e to the x power. So if I'm doing e to the x power and I'm showing growth, when x is 0, e to the 0 power is 1. And then if my x is 1, e to the 1st power would just be that number, 2.718. So it would look like that. And then if I was using negative x as my exponent, well, there's no negative 0. 0 is still going to be 1. But if x is 1 now, that means e to the negative 1 power, which is 1 over 2.718, which is going to be 0.368. So that's where I got these numbers that I graphed here. And it's just to show you again, growth still looks like it's going up. Exponential is still falling from left to right. So it still follows that pattern. We're going to play around with actually graphing. So because these are both positive, we have growth here. And then I am going to need to make a table. And this is just really use a calculator, so I'm going to do it all in one step. I'm not going to do like I did before where I raise it to a power and then multiply it by 4. I would just go through and plug these in my calculator. And who are we kidding? We're not going to even do negative 2. Before it made sense because of the symmetry when we were using fractions, but we're not going to use fractions anymore, so I don't really need to include that. So I would just simply go through and plug each of these in the calculator. So if I do e to the negative 0.5 power, and then I multiply that by 4, because there's a 4 there, I get 2.4. If I raise e to the 0 power, because 0.5 times 0 is just going to be 0, I'd get 1 times 4 is just 4. And then first power, so that would be e to the 0.5 power times 4. So that's going to be about 6.6. I kind of jam these two close together. And then let's see, 0.5 times 2 would be 1. So the next one would be e to the first power. And times 4 would be about 10.9. So now I'm just going to go ahead and graph these as best I can. So negative 1 is between 2 and 3. If x is 0, y is 1, 2, 3, 4. 1 is 6.6, 4, 5, 6, about 6.5. And then 2 is almost 11. So you could notice from this, I still have that same asymptote at y equals 0 or the x-axis. My domain is still all real numbers. My range is still y greater than 0. We're still dealing with an exponential function. And my asymptote is still y equals 0 or the x-axis. So all of that information is still the same. We'll just do one more quick graph. For this one, it says an x plus 2 and then a minus 4. So remember, in the x direction, it always does the opposite. So this is going to be moving 2 left. And this minus 4 means 4 down. So when I make a table, I would do what I did before, where my table, I'm using x. Let's do negative 1, 0, 1, 2. And then I'm going to do e to the negative 1.5 x power. And then I'm going to have to shift all the points. So then I'm going to shift them 2 left and 4 down. So if I put a negative 1 in for x, negative 1.5 times negative 1 is 1.5. So I would expect that to be a little bit higher than e. When I plug it into my calculator, I get a 4.5. When we use 0 for our x, 1.5 times 0 is just 0. So e to the 0 power is 1. So this one, e to the negative 1.5 times 1. So e to the negative 1.5 power is about 0.223. So I could already tell 2 is going to be too small. If I'm already down to 0.223, then I don't even want to graph the last one. So I'm going to go ahead and erase that off my table. So these are the points I would need to graph. These are my x's and y's. But then remember, we have to shift that graph. And we have to then shift it to left and 4 down. So I can't forget about that. So I need to go ahead and graph first. So -1 is 4.5. 0 is 1. 1 is this fraction. But then I need to shift all of those points to left and 4 down. 1, 2, 3, 4. 2 left. 1, 2, 3, 4. 2 left. 1, 2, 3, 4. And so I have essentially shifted down that asymptote also. My asymptote is going to be here now. And here is my graph. Got a couple problems left here. Let's see. Now we're going to look at, oh, and we should do our domain and range again. So our domain again here is going to still be all real numbers. The range is a little bit different, so I think this is a good one to do. My range is now everything above 4. Remember, I shifted that asymptote, so y is greater than 4. And my asymptote is now y equal to 4. So now we're going to look at continuously compounded interest. So we looked at in 7.1 when interest was compounded semi-annually or twice a year. If it was compounded monthly, which was 12 times a year, or quarterly, 4 times a year. So we were given that amount, that n. And this time we don't have that. This is continuously compounded. And remember, we talked about how E was our continuous growth base that we use. So this is the formula we're going to use. P is our principal or our initial amount. R is our rate as a decimal. And T is our time in years. And A would be that amount of money we have after those 2 years. So now we're going to practice using this. You deposit $3,000. So that's going to be our initial amount. So I'm just going to write down my formula really quick. I can remember this one because there was a shampoo called Pert for a long time. So I just remember A equals Pert. So my principal, my initial amount is the 3,000. My rate is the 3.5%, so that'd be 0.035. And I'm compounding continuously, which means we're going to use the E formula and not that other formula with 1 plus R over N to the NT power. We're not using that. We're using this E formula. What is the balance after 3 years? So T is going to be 3. And so A equals 3,000 times E to the 0.035 T power. Oh, but T is 3. And now I just go ahead and plug that into my calculator. And you should get $3,332.13. And this is our last example.